So now as a little bit of a change of gears, we'll look at structural estimation. So this is something that we looked at a little bit basically about 2 weeks ago, and well, now we're going to look at it in a bit more detail. So this was actually one of those landmark papers in a way. They triggered a lot of new work and use those techniques. And if you think about it, it's actually really, really simple. Yeah, in hindsight. So here's what they did. They took the following loss function, L of x, y, and f. The soup over all y prime and y, f of x and y prime minus f of x and y. So this is basically like a margin. The correct label, it's the largest, that's the largest score, plus delta of y and y prime. So that's basically the error that I incur by, predicting y prime rather than y. So you can think of that as, a loss-weighted error, so loss-weighted margin. So you can actually recover the binary margin from that. In this case, essentially what we have is, y can take on only two different values, namely 1 and minus 1, and delta of y and y prime is 1. If the labels disagree and 0 otherwise, let's just actually rewrite it.
So what is delta?
Delta is my loss. And in the binary classification problem, that's just 0, 1, let's say. But it could be anything else if you wanted to. So let's derive binary here. So delta of y and y prime is just delta y, y prime. Now, f of x and y, I'm just defining it to be y times f of x and y's intercept plus minus 1. So in that case, the soup over all y's is plus minus 1 of y prime f of x minus y times f of x plus delta y prime. Well, what's that? Well, we basically only need to evaluate two different cases. In one case, y equals y prime. In that case, this is 0 and this is all 0, right? So we have the max of 0, and now if y is not equal to y prime, then this is basic, then y prime is minus y. So we have minus 2y minus 2y times f of x plus 1. Bingo. That's up to a factor of 2 our, basics of margin.
Are you sure?
I think I am. Well, actually, let's just pick that 1/2 here. So we have 1/2 there, 1/2 there, right? So the 0 doesn't change. We have here this. And so the function of, let's plot y times f of x. So at 0 it takes on the value 1. If y times f of x is 1, then we have minus 1 plus 1 is 0. Everywhere here it's 0. And this is basically this function.
I mean, just maybe I make a mistake, but if you think about the super norm letter 9, consider about the to the next middle one. Suppose y equal to y prime, right? So
Yeah.
the next term is like 1, the delta is
Well,
1, and the formal time will be like 0, so it should be 1.
Okay, so the thing is, if y equals y prime,
This one is 1, right?
okay, yeah, okay,
define
sorry.
what delta does.
Oh, okay.
Problem solved.
Okay.
Yeah,
that's
otherwise this would be a very weird loss function to have, right? Sorry. Sorry. Yes. You guys are paying attention. This is great. Back. Yes. Now the other thing that you could have done is you could have rescaled everything by this delta, and you could have gotten exactly the same expression out. So for binary, at least those three are equivalent. In general, they are. And well, both of those things actually majorize this misclassification loss. And remember, we proved that. And the way how you prove it is very simple. Well, you just pick the argmax of, x of x and y prime, this guy here. You plug it in there for this y prime. Now this is, of course, less equal than this entire expression. Now, for that argmax, this is greater than that, so we can get rid of it. And this is just our loss. That's the proof. And then, once you have this, now the world's your oyster, right? You just, identify an interesting estimation problem with structured y. You design some function f of x and y that can be efficiently maximized with respect to y, for which you can find some cool algorithm that does this. You design a linear function space for f. You look at a tractable loss that is somewhat related to reality. You then actually go and solve this optimization problem. You write a paper. And I'm going to show you in 2 instances how this works. So, since you may actually at some point have seen the Tasker, Western and Collar paper anyway, or at least I'll point you to it, let me show you something that you might not have seen, namely graph matching. So, if you do computer vision, then graph matching is actually a really useful primitive. Right? And not just there, but also in like chemistry and biology. So maybe you have molecules in the database, you want to match it up. Regulatory networks, you want to estimate functions of proteins. Computer vision, basically, there are so many cases where graph matching is a really useful thing. But then you get that kind of stuff, and at least it took me more than a second to realize that these 2 graphs were identical. Just need to swap things around and then it works. But given that it's not so easy for humans and for computers, it isn't quite so easy either. So you have this is a problem. You also have that. In some cases, there are just so many different matches, and they all might work. Now, graph matching is at the moment, it's not quite clear whether it's really NP hard or not, but at least if you have a quadratic assignment, it is.
Can you explain what you mean by graph matching?
Well, so what it means is I have 2 data structures which correspond to graphs. And the vertices might have some different ordering. And then I want to find out, whether I can map one of the graphs into the other. And I might, for instance, through that, be able to find out whether 2 graphs are identical. So that's the graph isomorphism problem. Or I might at least want to find a mapping that is most similar. So where might you get this? Suppose I am studying, some regulatory network in a chimp, and I study the corresponding regulatory network in the human. There's a pretty good reason to believe that the chimp and the human have similar networks, but they're going to be subtly different. But if all the genes look a little bit different, I don't quite know exactly what maps into what, and so it would be really nice if I could have somebody that, maps those 2 networks. Or in computer vision, here's a problem. So I have 2 3D, just 2 images of an object, and I would like to be able to actually map them to each other. And well, that's not always quite trivial. Yeah, okay, sure, that window maps into this, and that one maps into that, but you basically now have a matching problem. and if I want to do things to quadratic. So why do I have a graph? Because at least I can assume that points nearby are probably close by. So solving that as a quadratic assignment problem is NP hard. Overall, whether graph matching is NP hard is at the moment an open question. It's, at the moment, I think it's a class of its own, and whoever proves things one way or another is going to be very famous. But basically, we don't really worry that much about the hardness here, but just say, well, actually, can we solve it as a linear assignment problem? Because if you treat it as a linear assignment problem, for that we know efficient algorithms, and as I'll show you in a moment, you can actually do a lot better. So let's just follow through with our recipe, right? This is actually something we did. So the first thing is, you need to identify an estimation problem structured by, okay, graph matching, this is it. Now, this is really hard, all that. So, whatever, let's just skip over that. Here's the good news. Now, quite often, graph matching isn't quite as hard as that, because you have attributes on the vertices, and you might only restrict yourself to a certain set of graphs that isn't quite so nasty, because a lot of the hardness comes from symmetries, and in some cases, local neighborhoods might actually do quite well to let you do the matching. So, in some cases, you actually have a lot of properly matched graphs. So, for instance, for images, you go and rotate them, or you have, stereoscopic cameras or whatever, and you know how things reasonably well match up. So you use that as a training set. So rather than solving graph matching in general, you solve graph matching in particular, namely graph matching for, let's say, for instance, computer vision for the problem that you have in your hands. Now that makes the problem a lot easier, and a lot of the pathological cases go away. And so let's just, set things up as a linear assignment problem. So we have graphs G and G prime with sets of vertices and edges. And we say that Gij is 1, we have an edge, otherwise 0. So what we now want to do is we want to find a permutation matrix pi that describes this match. And of course, a reasonable assumption to make is that they have the same number of vertices. Otherwise, I right away know, well, you can't find an optimal match anyway. So then I would like to have some compatibility function Cij, and Cij is large. Okay. In this case, well, it would be large if I is very dissimilar to j, and small if it's similar, but I could also set it up the other way around. Now, if I have attributed graphs, then graph matching is trivial, right? So if they all have unique attributes, let's say I have a copy of Facebook, the social graph, and have another copy of the Facebook social graph. Matching those two graphs is trivial, because an Alex smaller occurs in both instances only once. There may be some Jane Does who occur several times, but most of the names are essentially unique. So matching those two graphs, checking whether they are isomorphic is fairly trivial. But in general, I want to learn this Cij. So here's what you can do. You basically, we already looked at 2 weeks ago when we looked at the Hungarian marriage problem, right? So the stable matching. We want to minimize for all permutations pi ij c on j under the constraint that those are integral. Turns out that you can relax and things like that. And if I already know some of the matches, well, this is also good, because then I just restrict the pi ij's accordingly. So now let's just look where we are in our recipe. Well, we've passed terms 2 and 3. We've already identified the problem. We've seen here's a function f of x and y that I can easily maximize. That's the trace of c times pi under these constraints. So this is now my function. These are the constraints of what the argument can take. And a linear function space on the Cij's is fairly trivial. Well, this will just take image patches from first image and the second image, and then I compute some score of that. Now, of course, in general, I can get some gradient modes like this, and okay, so we can actually just quickly skip over that. We can also skip over the quadratic assignment part. This is just really nasty. But the point is basically, you want to be able to use efficient linear assignment codes rather than something that has to deal with that type of a matching problem. Question here?
Circle linear can't be used just by
So, yes, so the thing is, yes, for, you basically want to do a bipartite matching, yes. That's exactly our idea. However, what turns out to be the case is that even for general graphs, you can actually learn attributes of the vertex and the neighborhoods. And then for, subclasses of those graphs, do a pretty good job. And the good thing is, you solve the problem, and verifying whether a solution is a match, you can do trivially. The only thing is that, you aren't always guaranteed to get the right solution. So, just a bit of an idea of, what else people do. Yeah. This is basically the alternatives. I hope you will never have to use them. Okay, so basically this is what we learned. So now, here's what we do. Remember, this is basically the original optimization problem. We would like to, find over the score C, that score assignment function such that, the error that's incurred by, the discrepancy between the identity permutation, which maps things perfectly, and, whatever permutation that we find, is minimized, where now these permutations, so the sum over our trained set of graphs, is given by, solving the linear assignment problem. So now we need to define a loss function, and one that turned out to be very pretty is I just basically count how many mismatches I get. So I take the difference between the identity between two permutations, and just count how many pairs they assign differently. So if you do that, you get that the Frobenius norm squared is just 2. N is the number of dimensions of this beast minus the trace of pi transpose pi prime. That's important, and everybody can see that right away. At least I couldn't. Let me just quickly rederive this. Well, the first thing we notice is that the trace of pi transpose pi is of course nothing else than the trace of the identity matrix, because permuting and then permuting back gives me the original point back. So the trace of the identity matrix is just n. Right. Everybody knows that. Now, pi minus pi prime squared Frobenius norm, that's the sum of all the squared entries here, is just, pi plus pi prime minus 2 now trace of pi transpose pi prime, right? Now this is exactly this piece up here, so that's why we get 2n minus 2 trace of pi transpose pi prime, which is what we have. So this is going to be our loss function that measures how well we do. It just basically counts, how many pairs do we get wrong. And of course, the direct problem is non-convex. So we have to use exactly that convex upper bound relaxation. So that's where we are now in our recipe. We've picked a linear function space. That's good. We've now found a loss function that actually happens to look fairly nice. As a matter of fact, it looks exactly the same way as what we had before when we were dealing with a linear assignment. And so, we can just do it. Do you guys still need to copy that down? Or you don't? Okay. Remember we had f of, well in this case I just write f of x and phi prime minus f of x and phi plus delta phi delta phi and phi prime. And here we have the soup overall phi primes. So this is nothing else than the soup over all phi primes. Here we have the trace of basically c of x transpose phi prime minus the trace of c of x transpose phi. That was the loss function that we had before. So this is in the permutation group. And then we have plus 2 times n minus the trace of phi transpose prime. This is great. Because we know how we can solve this, right? The only pi prime dependent terms are this one and that one. And so we can actually pull this thing over, right? So the problem that we need to solve is trace of c of x minus pi transpose pi prime. And then we're done. So this now allows us to compute the loss function. And if we have the loss function, we can compute its gradient. Again, that's fairly straightforward because the gradient with respect to the c function simply means we compute the soup here, and then we get the subgradient by just plugging in the argument. And once we can compute the gradient of the loss function, we can, for instance, do stochastic gradient descent or distributed subgradient procedure, where we compute all the gradients, take an update step, compute the gradients again, and keep on going. Yep.
So, what's the constraint here that we get by injective one-to-one matching?
Well, that's the constraint that this pi prime is in the symmetric group, that it's a permutation. And since it's since if it's a permutation, it means it tells me that coordinate 1 maps into, let's say, coordinate 5, coordinate 2 maps into coordinate 3, and so on and so on, and no two coordinates map into the same place.
But how do we estimate that?
Well, that's exactly what the Hungarian marriage algorithm from 2 weeks ago does. Remember at the end when I showed this algorithm about the Hungarian marriage? That's the one that you need to use. So it's an integer programming problem, and you can show that you can relax the integral constraints, and you get the linear program back. You can either solve the linear program, or you use some other tricks for it. In practice, use existing codes. don't try implementing it yourself, because it's actually a fair amount of work to do it really well. Okay. Yeah. So one way, for instance, to think about how you solve those Hungarian marriage problems is well, essentially, suppose you start with some marriage, assignment of one graph to the other vertices, or and then you basically, figure out, well, this couple would be happy with some other swap, and you need to find an entire swapping cycle, such that nobody is partnerless at the end. And if you can find such swapping cycles that make everybody happier, and you follow through on that cycle, you keep on doing that until you can't find that anymore, and then you know by definition that you've achieved optimality. So there's a paper by two guys, one called Jonker, the other one called Folgenant, which explain that in more or less clear ways. It's not easy reading. Yeah, my handwriting as well, maybe. But I need the paper. So that has some of the more efficient algorithms in it. So this is essentially how you go about it, right? So now we have this tractable loss. And we need to solve the optimization problem, which is what I just showed you now. And at that point, you take your graphs, plug them in, and iterate. So, just as a refresher, remember when we had, just a risk minimization problem, one way to go about it is by doing a subgradient descent method. So you could do stochastic subgradient descent. So you basically take one pair of graphs, come up with a current list matching, find out, this is where things went wrong. So you basically solve this. You get an update in your parameters, basically in these f's. So that's basically updating the c's afterwards. So you essentially update the c's based on, how much the correct permutation differs from the one that you found. Then you move on to the next instance. And that's how you cycle through the graphs. And then as you drive down the learning rate, you converge. So it's reasonably straightforward. I want to show it to you for permutations, because permutations look like something very strange, where you would usually not think you could easily optimize over them and find an estimator of permutations, which is basically what this does, but you can. Now, permutations are not only useful in the context of graphs, but also for web page ranking. This is actually where this entire research started, by wanting to find a ranking of web pages in such a way that the most relevant web pages are on top and the least relevant are on the bottom. Now, it so happens that people in information retrieval have fairly outlandish and, well, to the uninitiated, strange-looking loss functions, which, determine how well your algorithm is doing. So they have names like normalized discounted cumulative gains score, and they are about as easy to understand when I first looked at them as the name is. Now, turns out you can basically rewrite it, and the math is identical to the graph matching problem. So, but yeah, there are by now better algorithms for ranking, so that's why I didn't want to go into much detail. Whereas for, well, graph matching, I think this is pretty much still state of the art. So I'm not going to go much through the actual slides here. It's just straightforward. So let me just show you a little bit what happens. So without learning, you get some matching by basically hand designing, some filters where it works okay well, but after you do learning, things work a lot better, and stuff is actually fairly reasonably matched. I mean, all the lines should be non-crossing if things were fine, but they aren't quite. But so you can see it gets the ends wrong. But besides that, it's actually a good matching algorithm. So if you then go and compare to what you would do in general, it essentially goes and beats everything else. And I mean, the specific numbers aren't really important. What's a little bit more interesting is this graph here. So if you look at how much computational time you spent, linear assignment and learning, this is the error rate that you get. It's very low, and it's the fastest of all algorithms. If you don't use learning, well, you get something that's fairly mediocre. If you use learning, you do better. This is an interesting data point. This is called graduated assignment and learning, where you then replace the simple linear assignment operation with something that's a little bit more complicated. So you're playing the trade-off between computation and accuracy a little bit further. This would be graded assignment without learning. And then quadratic assignment, well, just for different normalizations, these algorithms actually are quite horrible. So, as I said, you can actually use it for a lot more applications. You could use it for ranking. And an interesting question, and I think this is actually quite related to a question that came up with office hours today, is what if I can have multiple matches? So the question that came up today was in the context of maybe something like airborne. So basically when you rent out vacation rentals over time, you might actually have users wanting to look at several items, but then on the other hand, if you're renting out an item, you might not actually want to have to look through hundreds of applications just because your service is really popular. You want, an intermediary to do some pre-sorting and, find out the guys that are already good candidates. So in this case, you essentially get the equivalent of a polygamous marriage, right? So basically each man is allowed to marry several women likewise. But the number of marriages in each case is fixed. So let's say they're all allowed to marry 5. And that also turns out to be, again, an integer programming problem. So at least in math you can solve that problem a lot more easily than in real life. And okay, so this would be actually a very nice application of it. So let me conclude with sequence annotation. And that's
question.
Yeah.
So you're solving for this matrix pi. And
Yes.
it's a relaxed version where it's technically linear, and you get from that linear optimality matrix to the actual assignment.
Okay.
But the row has like all uniform 21, 21, 21.
Okay. So this is exactly one of those cases where total unimodularity helps you. So remember when we looked at why you can do a linear programming realization. So if this is my grid, so those in the back row might have to squint a little bit, but basically imagine there's a grid. So this would be, a problem in 2 dimensions. And I just don't want to draw more than 2. So now, in such a grid, if my constraint set looks like so, goes from, make sure it's a polyhedral set. Right? So what I can see is that all the vertices here are integers, are integral. In which case, if my linear program, has this as a direction vector, and I'm going to pick this point here, right? Because this one is most aligned with this vector. So this is my optimal solution of the linear program. And all I now need to prove in order to show that the integer linear program can be relaxed is to show that all the vertices of my constraint set are integral. So if I had something of this form, right? If my constraint set looked like so, then the integer linear program still would get this point as a solution, but that extra spot would mean, this extra space would mean that my relaxation would not be integral anymore. But for the marriage problem, or the assignment problem, whatever you call it, or likewise the polygamous marriage problem, the constraint set has integral vertices, and that's what you're saying. That's the idea. So that's what goes under total union modularity. It's a very beautiful property. If that isn't clear, by all means have a look at the optimization slide deck, and there's a bit more detail in there. Okay. Any other questions? Good. Now let's move on to sequence annotation. So, let's first look at the simple classification problem. So I have lots of x and y pairs, and so I want to estimate the y's given the x's, and that's just fine, right? But now what if these y's were actually correlated? So for instance, I have a sequence annotation. I have a sequence, and I want to find out whenever somebody is running, and then I want to find out when they are just walking in. So I might want to do activity segmentation. Right? So basically, I have these correlations here. The question is, can I actually exploit this for estimation? That's an obvious yes, otherwise I wouldn't be showing you those slides, right? So that's again step one, identify problem. Okay. So now we need to define a f of x and y on the sequence. So there's the problem. And the thing that, so if I just have things independently, then I just define f of x and y to be sum over yi f of xi. In which case, finding the optimal labeling is trivial. I just pick yi to be the sign of f of xi, right? That's trivial. Because now here they're independent. Now if I add to that an interaction term, some f of yi and yi plus 1, then this might, for instance, ensure that adjacent yi's will be more likely to have the same label. So who has done dynamic programming before? Good, because we're going to do that now. So you can just lean back and relax. Yes?
The correlation is not between x's.
No, the correlation is between the y's. I mean, there might be a correlation between the x's. There might be actually a lot of correlation, but I don't need to know about it explicitly, or at least I don't need to model it, because I'm already observing it. See, I'm already observing the x's, so I don't need to model them, at least not necessarily. And then all I have to do is just make sure that I model any correlation between the y's properly.
Because if there is a correlation between x, choose action.
So, okay, so this is a good question, why wouldn't you want to, for instance, choose like a hidden Markov model, right? Who's good at recognizing pictures of cats? I think everybody would say yes. Everybody, if you see a picture of a cat, you'll be able to tell it's a cat, right? Okay. I mean, unless you had way too much beer. Now, who's good at drawing pictures of cats? Not so many. I mean, I'm definitely not. So now, what this simple check just did is I checked whether you have a good discriminative or a good generative model of a cat. So I think all of us can safely confirm that they are able to tell cats from other animals even under a lot of duress, but I think very few of us would be able to draw really good pictures of cats. So this is basically the difference between having a generative model, like the hidden Markov model, which would, I mean, we're actually going to do a lot of generative models later on, but basically here I can get away by avoiding it. And a discriminative model, which is one which just tries to actually recognize, in this case, some labels, namely those y's, given the x's. And so this is why I don't have to model the dependence between the x's very much. I can only exploit that for coming up with a better estimate of the y's if I wanted to. So this is basically the function I'm going to use, yi f of xi. So this is like my classification problem. Then I have this function f of yi plus 1. In a good old C++ notion, I've overloaded the argument here. So this is obviously running some different piece of code to evaluate yi plus 1 rather than xi. And I'm just going to call this thing here g of yi plus 1, which of course depends on the x, but doesn't matter here. So I have this function here. Now the question is, can I maximize this? Because if I can, then I have a sequence labeling. It doesn't necessarily mean that this does something useful until I've actually figured out how to set the values in G. But at least this is a mechanism that will produce a sequence of bits. I want to maximize this. Okay. Now what I can do is I can just split up the maximization over all the y's into 1 over the second up to the nth element, and 1 over the first element. So far so good. And I can split up the sum here into something that depends into g of y1 and y2, and the sum of the remaining g's. And since this entire expression here depends on y1 only in there, I can just pull the bracket, right? I can just reclose this. So I can pre-solve. I mean, of course I don't know what value y2 has, but if I knew y2, I would sure know how to pick y1, right? So now let's basically, for every value of y2, pick a value of y1, and I call this function h2 of y2. But now something magical has happened, right? Because I've gotten rid of my maximal y1 problem. And I only have a function of y2 here, and a corresponding term there. That's it. Then I can repeat this procedure, right? And I pull out the maximization over y2, which now takes 2 arguments. h2 of y2, this guy here, and g of y2, y3, this guy there. And the rest is basically just junk up. And then I get rid of y3 and so on until I'm at the end. This allows me to maximize this expression. So now I've maximized it, and at the end I will know what the value of ym is. Let's say it's 1. At this point I can go back, and I can look up, given, because I had to solve this for, ym, I can figure out what the value of ym minus 1 has to be if the value of ym is 1. So after value of ym minus 1, I work my way back to ym minus 2, and I keep on working my way back all the way to y1. So you basically solve forwards, then you back substitute the solution in. And it's a good idea to keep that table around, which basically contains pairs of, well, if y2 has this value, then what would y1 be? If y3 had this value, then what would y2 be, and so on. And this is the very simplest case of dynamic programming. Any questions at the moment? Because this is going to be a technique that we're going to use over and over again. Okay. Now, one obvious thing that you could do is you could start at the end, right? So there was no reason why I should have started in the beginning. And I can basically do a backwards pass. As a matter of fact, if I have 2 processors, I could start in the front and at the end. And at some point I will meet in the middle. This algorithm has a name in numerical in algebra. It's called the BABE algorithm. Burn at both ends. Okay. Now, let's assume that we have a very simple loss function, namely just count how many bits we get wrong, and then all you have to do now is just solve the argmax problem. This guy here. Solve the argmax over this. That gives you the subgradient then afterwards. You update maybe the stochastic gradient to the same procedure, and you iterate. That's exactly the same procedure as what I showed you before with the permutation, except that now rather than invoking the Hungarian marriage algorithm, you have to dynamic program. And chances are, if you took a theoretical computer science class, that maybe there are some cool optimization algorithms that haven't been used in this context yet, and you can probably still write a paper about it. Now there are lots of extensions. And by the way, this has been really successful, and a lot of people have gotten best paper awards by essentially using this procedure in their context. So for instance, you can use this for face detection. And if you know that there's at most one face in an entire image, then rather than looking at each window in isolation, you look at all the windows and you pick the best one. Right? Okay, nice problem. You can look at segmentation. You can look at named entity tagging. You can look at sequence annotation. You can look at segmentation of phrases, where you say, well, I want to find out where phrases end. Well, this matters in basically a lot of Asian languages quite a bit. Or you can try to determine what swimmers are doing. So this is something that we did, where we basically strapped accelerometers onto, well, essentially Olympic athletes. And they swam in the pool, and you wanted to find out when they're doing what. Because what people usually do is there's a coach, and he sits by the pool with a stopwatch and measures each stroke or how long it takes. And he has a big logbook and writes it all down. And this is excruciatingly boring. And this way you can all automate it. It's actually more accurate than the coach. And basically makes the swimmers go faster. They know when they're slacking off. Now there are a lot of extensions. And I'll just quickly finish with that. So one is you can basically have what's called a structured rank loss. So this is where you basically have, let me draw a picture. Remember, this was our loss function for rank loss, right? So hinge loss, right? This was 1. This is y times f of x. 1 as well. Okay. Now, the actual binary loss for misclassification was this guy here. And if you look at it, yes, this sort of margin loss is a really great idea around here because it's a convex upper bound and everything works out nicely. But once you move beyond this point, you end up overestimating the loss of these instances. Now that's not very good, because if you overestimate it, you give instances way too much weight, and you basically try fixing instances that are going to be wrongly classified anyway. That may not be in your best interest. So what you can do instead is you can say, well, actually let's just give up on those instances and come up with this ramp loss, which basically goes like this of margin, and then continues straight on. So in other words, you just clip the loss between 0 and 1 as of margin loss. So you do this, then you might wonder, how can you actually efficiently optimize it? And that turns out to be simpler than one thinks, because you can, for instance, use the concave convex procedure. So that's something that we briefly discussed, I think, in the optimization class. Let me just refresh what's going on. Let's say I have some non-convex function here, and I want to minimize it. And I can write this as a convex function plus a concave function. Now, at that point, well, minimizing this convex function is really easy, right? Minimizing the concave function is not easy. But since there's a concave function I know, then I can just perform a Taylor expansion at this point. It's going to be an upper bound. So I'm going to minimize the convex function plus the Taylor expansion on the upper bound. I solve the problem. Then I go and compute a new Taylor expansion and keep on doing this. So I'm successively solving for tighter and tighter upper bounds on the concave part. And this has 3 or 4 different names in optimization. It's called a concave procedure, convex concave procedure. So CCCP, you can imagine that was written around that time, right? So if you remember Cold War times, right? By Yulin Rangarajan. It's also known as DC programming, difference of convex function programming, and that predates this by about 20 years. It's also called, I think, the K method in yet another community. And it's called, you can actually show that in quite a few cases, the EM algorithm, the expectation maximization algorithm, is a special case of this. So it goes by 4 different names, which is kind of funny. But anyway, so now how do we decompose this into a convex and a concave function? Well, that's very easy. We just take this function here, and then we take as the concave part this here. Now we can solve the problem. So let's see what happens if we solve it accordingly. So initially, we're over here, so this part dominates and this is just constant. So we solve a standard SVM problem for binary classification. Then we look at all our instances, and all of those that are correctly classified, I keep everything the same. All of those that are incorrectly classified, well, what's going to happen? I'm in this branch here, and by the way, there's this linear upper bound. At which point, it just so happens that I can, well, just throw out the instance. So now, the upper bound here is a constant function. So, in other words, you go and solve the classification problem. You throw out all the errors, you resolve. You then check which ones are the errors and you keep on iterating. Which is an insanely simple algorithm. So, at some point, many years ago, we actually looked at this algorithm as a student, and we looked at each other and we said, this is so simple, we'll get it rejected at a conference. So we decided not to publish it. That paper, with a few variations submitted by somebody else, got the best paper prize. And yeah, I mean, they did great. They deserved it. But so, big lesson: if you think something is too simple, still try to publish it. In some cases, it might look very simple for you, nobody else. Now, this has been something that we actually did as a follow-up because we were a bit frustrated about this. So you can actually extend it to multi-class. Now, if you think about it, you know, okay, let's just, if we had a y in here, right, then this would be our standard structured loss. But actually the structured loss suffers from the same problem, namely as the function values get really large, it very much overestimates the current loss. So what you can do instead is you simply, you know, clip it by, rather than plugging in f of x and y with a correct label, you know, subtracting from it the maximum of x and y prime with any label. This is still an upper bound on the true loss. You can see that by just, you know, plugging in the appropriate values here. But it's a tighter upper bound. And at that point, you have this loss ramp. You basically have a, you know, structured ramp loss. And it turns out, so this was very much of a surprise, but it's not even a complex problem, you can prove that this loss is consistent, whereas the original structured loss isn't. So that's something that David McAllister and I forgot the name of the second author, his last name is Keshet, proved at NIPS in 2011. So basically this is actually the legal loss function. Another thing, you can use invariances. So in some cases you don't only have the data, but you know that under certain transforms the data remains approximately the same. And rather than attacking it with, you know, heavy duty tools from, you know, math in the form of, you know, group theory, you don't necessarily always know that, you know, the data actually is entirely invariant under those transformations. So for instance, if I have, you know, an OCR'd image, then I know that certain brightness transformations essentially should leave the image the same. Yes, it's going to be a little bit harder to recognize things, but, you know, the digits are going to be the same. Except that at some point, once I, you know, reduce the contrast so much, I won't be able to recognize anything anymore. Or I add too much noise, or slant, or deslant, or, you know, do all sorts of other transformations. So in this case, well, wouldn't it be nice if we could plug that into our loss function as well? This is our standard structured loss. And now what I'm doing is I'm simply taking the soup not only over all labels, but over all G, where G are basically transformations of the data. And they might be applied to X. They might also be applied to the labels. And I mean, there's not enough time that I can go into a lot of detail there, because this would be a slightly different machine learning class. For instance, these transformations could be edits that a spammer applies to an email in order to break a spam filter. And so you could say, well, you know, spammers are allowed to only change, you know, 5% of all words. How would you train your classifier in such a way that even under these transformations, the error is fairly resilient? And that basically what it does is it ensures that not a single word gets an extremely high weight, which is exactly what you want. Because in that case, you know, the spammer can just leave out that word or add that word in order to completely break things. Or you might actually have, you know, an object recognition problem. You have an entire bank of Photoshop or GIMP filters that you can apply to it, and you want to make sure that the image almost remains the same. And of course, if your filters are very distorting, then you don't want to punish your, you know, your function too much if you get it wrong. So those things are fine, for instance. So what this did, amongst other things, it, you know, superseded quite a bit previous work on invariance transforms, where people derived very expensive second-order cone or semi-definite programs, whereas with this now you can, you know, simply parallelize it, and it's very straightforward and efficient. So there's a paper review. I'll be pointing to that in a moment when the slides go. So for next week, here are a few links, and yeah, basically good luck for next week. So some pitches for how you pitch to VC, or write a grant proposal, or overall, I have my criteria. There's a lot more along those lines. Essentially, make a convincing argument why what you're doing is really cool, and why you care, why everybody cares about it. Okay, so those slides will be up by tomorrow. And practice. Okay, good. Any questions?